It's my pleasure to introduce our speaker, Renyuan Xu from University of Southern California. She is currently an assistant professor there, and her research interests lie in the machine learning theory, mathematical finance, generative models. In this talk, she will be speaking about neural network-based score estimation in diffusion models. Renyuan, the floor is yours.
Thank you very much for the very kind invitation, and thanks for having me here. I'm very sorry that I can't come in person to attend this workshop due to visa issues, but I'm very happy to have the opportunity to share this recent work with everyone here via Zoom. So this is based on a recent work with my student Yinbing and my colleague Mason at USC. And the paper has been, the short version of the paper has been accepted by iClear this year, and we are working on a longer journal version. So I will be talking about optimization and generalization perspective of the training of diffusion models. Okay. And due to the last talk of today, so I didn't put a lot of intense contents in my presentation, and feel free to chime in if you have any questions, comments, or thoughts, and I would love to keep the talk or presentation more interactive. Okay. So for the motivation part, I'll be really quick because everyone knows about the benefits and advantage of diffusion models. So generative diffusion models is one of the most successful generative models in the past few years. It takes training data that we would be interested in generating more, and then we feed the training data into the generative model and hoping to create more similar and natural looking pictures or samples that we're interested in. And successful applications include creative arts, chatbot, and data creation such as financial and healthcare data. So we have a lot of successful applications of generative models, including diffusion models. So the key question of this era of generative models is that how could we create good new data given samples from an unknown distribution that we have access from? So diffusion probabilistic models is popularized by Song and his co-authors in 2019. And we have quite a few successful examples, as we mentioned, including DALL-E from OpenAI and some follow-up products. So the idea is that we want to create data from noise by reversing a suitable chosen dynamics. And practically, the advantage of this very nice idea of using diffusion processes or reversing a suitable dynamics include better data quality. This is what we've seen from practical applications. Also, we observe more stable behavior in training compared to other generative models. It's less prone to model collapse issues, as well as other issues. And also because we are reversing a chosen dynamics and there's a time index of the dynamics, we also have interpretability in the intermediate representations when we reverse this chosen dynamics. So it helps us to understand if things doesn't work out, it helps us to understand what may be the possible issue through looking into the intermediate representations. So these are all the benefits of diffusion probabilistic models in terms of generating data that we're interested in. So this is one of my favorite examples of diffusion models. It's the original version of DALL-E. It helps to continue an image beyond its original border. For example, if I ask DALL-E to create a continued picture of my favorite painting, then I can just type in the word saying that, oh, put this nice lady with a pair of a pearl earring into a kitchen, and I want the background to have a consistent style of the original painting, then DALL-E is able to create this new art for me. So this is one of the most favorite example for for me. And if we put everything into a mathematical framework, then we have this forward dynamics in continuous time. So it's a diffusion process driven by the drift term B and volatility sigma. Then for us, if we want to use diffusion models to create samples, then the first step is that we want to fix a time horizon t. This is often large, and I'll explain later why we want to have a large t. Then we sample x capital T. There are cases that we know the exact conditional law, so the simulation of the forward process would be easy. Then in the second step, we want to run the time reverse process x bar starting at x0 bar that follows this distribution. So we denote PT as the density function of x capital T here. And then we run the time reverse SDE for the same time horizon. And we hopefully we want to get a data x T bar that follows the desired distribution we want. The key idea is that we have a forward process and we also have a time reverse SDE. So forward process is driven by Brownian motion, BT, and the time reverse SDE is driven by a different Brownian motion, BT bar. So having different noise process will help us to generate a picture xt bar that is different from x0, but it follows from it is sampled from the desired distribution we want. So we want xt and xt bar to have the same law, but they are driven by different noise process. So we simulate something different, but from the distribution we want. So this is the key idea behind the diffusion model, and this is the mathematical foundation that could support us doing this forward and backward procedure. Is there a question?
No, everything is good.
Okay, then I'll continue. So the first question is what's this xt bar process? What is this time reverse SD? Is it simple? Is it easy to simulate? And is it easy to analyze the regularity property of the backward process? So the form of the time reverse DE is a classic result in the stochastic process literature by Anderson in 1982. And Hausmann and Perdox in 1986. So the result says the following: if we use PT to denote the density function of xt, and if we define the x bar process as the following, driven by drift B bar and volatility sigma bar, then under very mild conditions, regularity Lipschitz conditions, then the process 1 will admit a strong solution and xt bar will have the same law as xt capital T minus T. Okay. So if we take a closer look at the dynamics 1, then we realize that, oh, the volatility term sigma bar is actually easy. It's just the time reverse of the original volatility term, but the BT term would be more involving. It involves the original drift term B, and it also involves the volatility term and the gradient of log P. So this is more challenging to handle. So there are a few examples that people use a lot in practice in terms of simulating pictures using this idea of generative diffusion models, because for all these 3 examples, including the OU process, variance exploding SDE, variance preserving SDE, we all have closed form solution of the conditional law. So for a given x0, I know the distribution of xt given x0. So this can help me to simulate the forward process in a very efficient way. And this has been used in practice a lot. I think there are empirical studies on what process would work better for what type of applications, and people observe there are applications that variance exploding SDE gives better performance, whereas for other applications, we may want to use variance preserving SDE. I think theoretically, there hasn't been any analysis to show, oh, what is the data distribution that works, that this particular SD would work better. But empirically, I think there are a lot of discussions on which one is better in practice. There's some comments on the examples here, and as I mentioned, the drift, the volatility term of the time reverse SD takes a very simple form, but the drift term is more evolving because we need to essentially, if we want to implement the time reverse SD, we need to estimate this gradient of log P term in order to implement B bar. And in the statistics literature, this gradient of log P term is also referred to as the Stan's score function. Okay. That leads us to the second ingredient of the diffusion models framework. So we want to learn this gradient of log P with the data we have, and this is called the score matching part in the diffusion model literature. And if we want to put it in an objective function, and we can considering this score matching objective function. So we integrate from a small time point delta to the final time horizon t with the weight function lambda t, and then we have this square loss function. So gradient of log P is our target, is a functional form that we want to estimate. And we also have a parameterized estimator as theta. We can use traditional regression method, we can use neural network, and we can consider other functionals, parameterized functionals as well. The key idea is that we want to minimize the theta term here so that as theta would be close enough to the gradient of log P so that we can implement this B bar term here. So that's the key idea. And also we want as theta to be close to gradient of log P for any time step in order to make sure that the law of xt bar is the same as x capital T minus t at any given time t in order to recover the desired data distribution. So we want as theta to be close to the Stan's score function at any time t. That's why we have an integration here. And the reason we have a small delta is technical, because when we run the time reverse SDE, when the timestamp is super close to 0, there might be some explosion behavior in the analysis. So people want to stop the process when it approaches to 0, to have a bit of early stopping, to choose a small delta to avoid that technical issue. Okay. Okay, so the summary is that we need to have a good estimation of the Stan score function using the amount of data we have, and to have a good estimation at any time t in order to recover the data distribution we want. So this is a key summary of what we want to do here. And if we summarize the entire data generation procedure, we have a few steps. The first step is that we want to find a good theta. We specify a class of parameterized functions, and then we want to find the theta so that as theta will be a good approximator to the gradient of log P. And then with the estimated score function, we first sample x0 bar from the terminal distribution for very large t. If we don't know the explicit form of PT, then we can replace this PT by a Gaussian distribution or stationary distribution of the process, because this forward process is of our own choice. So if we take a simple forward process, then sometimes we are able to know the conditional log, sometimes we don't, but we can approximate this PT when t is large, the error would be small. And then the third step is to run the backward process until the same time horizon in order to simulate data. And if we want to compare the original data distribution, we have access to samples from versus the distribution of X capital T bar. This is the data that we simulate using these diffusion models. Then we can see that errors appear at several different levels. In the case of 2, where we sample X0 bar from the density function of X capital T, then we only have the score matching error here. Okay, so it comes from 2. But in the case of 2 prime, where we approximate PT by some noise distribution, then we also need to make sure that the mismatch between PT and P noise should be well controlled. So this error part won't explode when we simulate the backward or time reverse process. So this is the second layer of the error. And also, in order to implement a continuous time SDE, there's also discretization error in the backward process. So the principle of the design should have a good trade-off among all these 3 different layers of errors. We need to make sure that after we implement the entire procedure, the error term between P data and the distribution of X T bar should be well controlled under certain distance function, either Wasserstein distance or other distance function. And this should be controlling these 3 different levels errors should be a key principle in terms of how we choose the drift term B and how we choose the volatility term sigma. So this is how I view this problem. It's a design problem of the diffusion processes. Okay, I'll pause here to see if there's any questions before I continue.
All good.
Okay, then I'll continue here. So there are some very recent literatures on how to trade off these error terms to design drift term B, volatility sigma, and how to choose the noise distribution if we can't simulate from PT. So under some different conditions on P data, whether it's bounded or have sub-Gaussian tails, there are a few very recent papers available on arXiv last year showed that the bounds of the distance between P data and the distribution of X bar T can be decomposed into 3 terms. First of all, the noise inaccuracy, so the difference between P noise and PT, this error term decays exponentially. So if we choose a long time horizon, this term can be well controlled. And also the second term is the score mismatch. So if our S theta has a huge error, then this has a huge impact on the quality of data we simulate because it depends polynomially on the time horizon. If T is big, then the error of score mismatch will have a huge impact. And in terms of time discretization of the SDE, it also depends polynomially on T. And also we have a polynomial term on the step size. Okay, and so this year there's a very recent paper by Wenping and his student. They showed that if they use Wasserstein bond between the diffusion model sampler and the target distribution, and they use some contractive diffusion processes for the forward process, then they can improve the error decomposition into the following term. So the noise term still decays exponentially, and the score mismatch term will contribute to the final error with the constant dependent term here. So they remove the polynomial dependence in T. If the forward process is good enough, it's contractive. And also they remove the polynomial dependence term for the discretization error. So this is the improvement. But what was missing in the literature is that how to design an approximation step and a learning algorithm, a low score mismatch error with a theoretical guarantee. So there are results, statistical results in the literature to show that, oh, if we have this amount of data, then there exists a neural network that could potentially give me a good approximation to the stance score function. But how to find this neural network? This hasn't been shown in the literature before we started this project. So what we really want is that we want to show the statistical guarantee, optimization procedure, and the generalization power all at the same time with the design of an implementable algorithm. So that's the idea behind the project. So in order to do that, we will focus on a very simple forward process. As I mentioned, this is very different from analyzing the mathematical property or foundation of diffusion process, because when we study diffusion processes, we want to have our framework as general as possible. But when it comes to the design of diffusion process, we can choose very simple process as long as it helps us to generate pictures. So it's really a design problem. So for us, we focus on a very simple time varying OU process. So the drift term GT multiplied by XT, and the volatility term is only time dependent. It doesn't depend on the state process XT. So we will stay with this simple formulation. Later on, I will show some benefits of this particular time varying OU process. Okay. And for this forward process, the time reverse SDE also takes a very simple form here. And we can write, if we specify the forward process like this, then the score matching objective function will have the following term here. So we just plug in the explicit expression of the OU process that we want to work with. Okay, so in this case, the gradient of log P will have a much simpler term. And essentially what we are trying to do here is that we want to estimate this F star function here. So we want to have a S theta that could well approximate a function that is associated with this F star. This F star is the conditional expectation of X0 given XT, and this is associated with a very fundamental formula in the statistical literature called Tweedy's formula. And we also get some insights from that expression as well. So what we can see here is that after specifying this OU process, we have a very simple form of the score matching objective function, very simple form, but still it's a bit difficult to train in practice. Can we further simplify this objective function or not? So what we realize is that the benefit of working with the time varying OU process is that we can further rewrite the objective function in the denoising score matching term. So these two formulas are equivalent. So the value of the objective functions are different, but the minimizer of this problem versus the original score matching problem would be the same. And if we take a look at this form, this is a much simpler form than it, and it helps a lot in terms of training. So if we take a closer look at this denoising score matching function, we can see that it's very easy to estimate because X0 is the original sample that we can observe, we have access to, and XT is just a perturbed sample that we can also simulate because we know the conditional law of X small t given X0. And these two observations tell us that this denoising score matching function is extremely easy to work with. The key idea is to find a appropriate parameterization for S theta so that we can solve this minimization problem. Another comment is that this nice observation of the simplified objective function has also been discovered in the literature in the discrete time framework, and we did the analysis for this continuous time framework to find this much simpler form of the objective function to work with. So in terms of the optimization part, we consider a very simple parameterization. So we want in order to match the second term and third term here, we take our S theta with the particular form. So we want to have a neural network, and the scalar in front, we have explicit expression for. And if we take S theta with this parameterization form, then the score matching problem is just a mean square minimization problem. So we have a neural network parameterized by theta, then we have a label we have a label function for each data point xt, and we try to find a theta to minimize this mean square error here. And equivalently, if we use this denoising score matching function, it's even simpler. The target function is just a noisy label, which is x0. So we view x0 as a noisy label of this true conditional function here. So x0 will be a noisy label for this conditional expectation, and we are trying to minimize this objective function here. Okay. So we translate the score matching problem into a mean square and error minimization problem, and we'll borrow some literature in the statistical estimation literature to try to help us solve this problem. So if we want to take a closer look at the form of the function here, and also how data contribute into the objective function, we can see that we'll view the data we have access to as the noisy label, and the true label we want to estimate come from Tweedy's formula. So it's the conditional expectation of x0 given xt, and we have some noise term. So the residual term is all hidden in the noise term epsilon here. And this is different from a usual regression or supervised learning problem, because first of all, xt comes from a diffusion process we specify. So this is an unbounded input. So xt is unbounded, and another feature is that we have vector valued output, because for usual regression, we want to find a y value here. But for us, x0 will be a giant vector because it represents the data input we have. So it's a vector valued output. So this is an atypical setup. So we need to modify existing results so that we could use them in our framework. But then we realized that many theoretically unaddressed machine learning problem can be actually formulated into this atypical regression problem or this formula. For example, if you are familiar with the state space modeling, which is a sequence-to-sequence generation that works very well for time series analysis, prediction, and generalization, or if you are familiar with a conditional GAN framework, all these two problems, if we want to analyze the key technical part, it can be written as this particular atypical regression problem. So that tells us that if we can build a theoretical foundation for this atypical regression problem, it can also help us to address some other machine learning problems, the theoretical foundation of them. So this motivates us to have a bit more understanding of this problem and then the developments will be generic, and we can apply it to other problems as well. Okay, in order to do this, let me specify a bit more on the neural network architecture and the optimization algorithm. So we consider a two-layer fully connected neural network. So there's only one hidden layer, and we use the ReLU activation function. So all the neurons would be connected in the final layer through the summation term, and we have a total number of m neurons. Here, we use the scalar 1 over square root of m, and I'll come back and comment on the other regime with 1 over m later on. So for here, we work with 1 over square root of m, and we want to, if we have n samples from the data distribution, then we are trying to find a theta to minimize the empirical risk function with n samples. So I want to comment a bit more here. So because we know that we can sample independent data x0 from the data distribution, and in order to have a good approximation for any time t, as I mentioned, having a good estimation for any time t is the key in order to recover the data distribution for the time reverse SDE. So in order to do that, we also sample the time step uniformly from this time interval here, and then calculate xtj from this conditional distribution. Okay, so we sample x0 and we sample time step, and then we simulate xtj, and then we find a theta to minimize this objective function, hoping that this would be a good approximator to the standard score function for any time t. So that's the key idea behind the design. Once we specify the loss function like this, then we run a gradient descent algorithm according to this form. So everyone knows this is a very simple updating rule here. Okay, and I also have some comments on the initialization. So it's a very standard initialization. For theta term, it's just a Gaussian initialization, and for the coefficient in front, it's a random flipping of sign. Okay, and so one comment is that if we use this two-layer fully connected neural network in the over-parameterization regime and run the vanilla version of the gradient descent algorithm, the key challenge lies in the analysis of generalization guarantee. In short, this means that we only train the algorithm with the finite number of samples. So this is an empirical minimization. So I train my algorithm with finite number of samples n, but I want my algorithm or my trained parameter to have a good property on the population level. I also want this original objective function under the expectation term here to have a good performance. Okay. So this is the key challenge part of the entire analysis. So in the literature, we see that if we want to do a supervised learning problem with finite number of labels, then we can achieve good generalization property using neural network and gradient descent type of algorithm. However, if we have label noise, so if the labels has noise observations, then regression problems may suffer from the poor generalization property because regression may overfit to the label noise. So this is the most subtle part that we need to take care of. Okay, in order to solve this challenge, our idea is that we use the neural network parameterization and we couple it with the neural network training with a kernel regression. And then we use the results in the kernel regression literature and couple it with the early stopping rule so that we won't overfit to the label noise, so that we have a good generalization guarantee of our formulation. And the reason why we have a middle layer of kernel regression is technical, because in the existing literature, kernel analysis has a set of richer results that we can incorporate compared to deep learning theory. So that's why, although we still train the neural network using gradient descent, but in the analysis, we couple the neural network with the kernel regression and try to boil down the analysis to kernel regression and then couple it with the early stopping in order to solve all those technical challenges. Okay. And so the key idea would be the following. So there are very well established results on non-asymptotic analysis of the neural tangent kernel. So that's why we want to use the theoretical analysis for neural tangent kernels to help us do the analysis. And so the idea is that we want to design a proper class of neural tangent kernels so it keeps track of what happens to the over-parameterized neural network, and it stays very close to the neural network so that we can do the transformation in the technical part. And this idea of transforming the analysis of neural network to neural tangent kernel has been used in the literature for fitting random labels or a finite set of labels, but it hasn't been used to do analysis for regression type of objective functions. And also score matching is a much harder problem than the usual supervised learning problem. Okay, and so these are some high-level ideas behind the design. And I also want to comment on the fact that another possibility to achieve this analysis is to do a mean field analysis, but this hasn't been explored in the literature. By mean field analysis, I mean taking the scalar to be 1 over m instead of 1 over square root of m here. So it would be a very different regime and analysis would be different, and there might be some benefits of using a different regime to do all the analysis here. Okay, so this is a side comment here. And so for our analysis, after deciding to use neural tangent kernel as the key tool to do the analysis, we can decompose our objective function into several parts and try to provide an upper bound for each term. So the first term is a truncation error. So we know that we work with the diffusion process. And if we specify a large enough radius, then the probability that the process will hit the boundary would be very small. This is well controlled. So we choose a radius r and then do a truncation error analysis so that we can only focus on what happens within this radius r, within this big ball in RD. Okay. And the second term is an approximation term. So we want to see whether the neural tangent kernel will have a good functional approximation power. So this is the functional approximation part. Another part is coupling. Because we couple our neural network with the neural tangent kernel, we want to make sure that they stay close with each other for any iteration, in any iteration. Okay, and the last term would be an early stopping term, because as I mentioned, we don't want to overfit to noisy labels. So we want to make sure that we stop early enough so that the final result would be good. So these are the 4 error terms that we want to put together to get a good final result. Okay. Okay, so the first part is that we transform the score matching into a kernel regression problem. And then, as I mentioned, the first step is to see whether the functional forms we specified by the reproducing kernel Hilbert space would be a good approximation term here. So how far away is the best estimator within this functional class is to our target function f star. So because we know that usually the functionals induced by the RKHS would be relatively smooth, and sometimes there is a gap that we do need to control because f star may not be as smooth as we want. In that case, we keep this approximation. Sometimes we can also assume that f theta lies in the functional class we specify, then there would be no approximation error and the follow-up analysis would be much easier. but we think this might not be the reality, so we still want to keep this error analysis here in case f theta doesn't have the good regularity we want. Okay. So first step is a universal approximation. Second step is to apply NTK-based analysis to show the equivalence between neural network training and kernel regression. And this part is more original, so we will keep the focus of the talk on this part, okay? And there are also other technical parts. For example, because we have a multi-output labels, and that's why we can't find existing results in the literature. So we need to develop a new set of Rademacher complexity in order to help us control the prediction level. And another step that we really need is that we want to have an early stopping rule for the kernel regression so that we can prevent ourselves from overfitting. So these are other technical parts that we need to address at the same time. Okay. Let us take a closer look at how we design the neural tangent kernel so that it mimics the dynamic of the training of neural network. So we specify curly H to be the reproducing kernel Hilbert space induced by the following neural tangent kernel. So we design the key matrices as the following. So we can see that it's really motivated from the neural network because theta 1 and A1 are the neural network parameters in the first iteration here. So we have theta here, which is the linear term inside the RALU activation function, linear coefficient, and A is the weights, how we combine all the neurons together. So the neural tangent kernel is really based on the neural network here, neural network parameter here. Okay, so we specify the key matrix in the following way. It depends on the values of the neural network parameters. And with this specification of the neural tangent kernel, what we can show is that the functional class induced by our NTK has a very good approximation power in terms of approximating the target function. And this error term can be controlled by this term here. So RH is a term that depends on the expressibility of the RKHS. And what we can have is that if the truncation term is big enough, then this RH can also be relatively small. So this term is entirely controlled by the radius we specify, how large we want to, how large the ball is so that we focus on. So this term is well controlled by the truncation radius. And the second term we want to make sure is that we want to couple the neural network training with the kernel regression. So we need to design how we want to update the kernel regression so they always stay together with each other through the entire training. So in order to do that, we will update our neural tangent kernel or neural regression with parameter gamma. So K is what we designed. K matrix is what we designed here in the previous step. And we only need to update this coefficient or parameter here. And this parameter is updated according to this specific form that involves the frame matrix of K. And if we update according to this particular heuristic, we can show that under very mild conditions, the neural network will stay close to our kernel predictor throughout the entire training. So for uniformly overall training timestamp tau, and the error term is controlled by the weight of the neural network. So if we are in an over-parameterized regime and M is big, then this error term can be controlled with an order of 1 over square root of M. Okay? So takeaway is that the over-parameterized neural network perform as a kernel predictor. So it behaves like a kernel predictor and parameters still very close to the initialization. So it's a lazy training regime in the language of deep learning theory. So it's a lazy regime. The parameters do not go far away from the initialization if we use the gradient descent type of training. So this would be the key takeaway of what's really happening here. And so if we put everything together, so I skipped the analysis of I skipped an analysis of the early stopping part, but if we put everything together, truncation error, approximation error of the reproducing kernel Hilbert space, and the coupling error between neural network and neural tangent kernel, as well as the early stopping, if we put everything together, then the final results we have is the following. So we can get a score, an estimator using gradient descent, and this S theta is close to the targeted Stein score function, and the error is on the order of n to the power of -2 over 2 plus d. Okay, so this is the first result on the generalization error because we focus on the population loss here. So this is the expectation. So first result on the generalization error, if we specify a particular optimization algorithm to be gradient descent, and we also specify the particular neural network form that we want to work with, and this order is minimax optimal. It matches the result in the non-parametric regression results. So we can see that we still suffer from the curse of dimensionality here because D would be the dimension of the data we want to simulate more. And the idea is that if we have a low dimensional embedding of our data distribution, so if data distribution comes from a subspace, then we may be able to reduce the dependence to the dimension of subspace here. But as for now, the result still suffers from the curse of dimensionality if we don't impose further structural assumptions on the data distribution. Okay, and in order to summarize my presentation today, the key takeaway is that we should really view the choice of drift term B, volatility sigma term, and the noise distribution term as a way to do a trade-off in order to achieve a small error between the data distribution and the distribution of xt bar, which is the distribution of the simulated data we have. And what we could do in this work is that if we specify the drift term like this, and with a time varying GT function and a volatility term like this, then we can make a novel link of the probabilistic diffusion models to a regression problem and neural tangent kernels under this specific choice. And then this enables us to establish the first algorithm-dependent guarantee. So it's not purely on the statistical side, but we also incorporate a specific optimization algorithm and see what's the generalization property. And there are also some ongoing work that have been working with my co-authors. The first one is to see whether Schrodinger bridge could help us if we specify a noise, a distribution of the noise distribution, but I don't want to suffer from this mismatch. So I find a Schrodinger bridge that can move the mass from the P data precisely to the noise distribution I specify. And we want to understand the robustness of Schrodinger bridge and distributional robustness, and also whether mean field analysis interacting particle could help us to accelerate the simulation procedure. So this would be the end of my presentation, and you can find the paper on arXiv, and I'll stop here to see if there's any questions.
Thank you so much, Renyuan, for the very interesting talk.
Thanks, everyone.
Do we have any questions?
Hi, thanks for the talk. So I guess I have the following question. So somehow the way that you kind of like set things up, you have this very rich class for like that you're kind of competing with for the Lipschitz function. So you end up kind of suffering this kind of standard burst of dimensionality kind of rate, both in terms of the statistics and in terms of the algorithm that you get.
You mean the D term, dependence on D?
Yeah, like X and D. So I guess you could take any other generative model, like you can take like a GAN or something, and like you will get basically the same rate and the same kind of like, algorithmic dependence. You could take your favorite KDE, you'll get the same rate and the same dependence. So like somehow, like in what ways sort of does this tell you when should you use like a diffusion model as opposed to anything else, like as opposed to a GAN?
Oh, that's a very good question. So I think theoretically, this is the best we can do. And as you mentioned, this minimax optimal rate can also be achieved by other architectures. I feel like this part in terms of sample efficiency among different architectures might be difficult to achieve theoretically. I think the reason is more of taking one step back, because empirically, we have seen advantages of diffusion models compared to other methods. Then can we build up a theoretical foundation behind it? This is more because I think the benefit is also more on the implementation side and stability side. I feel like maybe like stability analysis, if we want to see if we do a perturbation in the data distribution, and we can see more things from that perspective. But in terms of sample efficiency, I feel like this is probably a bit harder to achieve, to compare sample efficiency. But in terms of stability analysis and in terms of which one is easier to implement and easier to train, then diffusion models has better advantages compared to other generative models. That's my understanding.
Thanks. Do we have more questions?
Thank you so much for the very nice and clear talk. There is some technical subtlety that I would like to understand. If you go back to the kind of estimation you did, maybe a couple of slides more. Let's see. Here. No, forward. There was a statement that that you said with high probability we were calculating some expectation there, and that where is it? Here. Yes. So when I look at the mathematical statement, for me this is a totally deterministic quantity. What do you mean that under mild conditions with high probability?
Oh, this is a very good question, because this expectation is taking expectation with respect to the law of xt here. So for example, if we take the expectation over x0 and over xt, then this is the rule of this expectation. However, we don't take expectation over theta. So the training of theta still depends on samples. So it's like we train a theta and we fix it. We want to see the performance of this particular theta with respect to the population loss. So the expectation is taken with respect to here, but we fixed the theta here. That's the high probability. High probability is for theta, but the population loss is defined for the input here. So that's
but you try now to decouple theta x when you use x to estimate theta.
So it's more like if I have multiple samples, multiple x0s, I use it to calculate theta. Then I fix this value of theta. And then xt, I take expectation to see what's the performance of this particular theta on the population level.
True, but again,
Mhm.
T will depend in X naught. Yes.
That's
For
true. That's true. That's true.
Theta,
Theta will depends on theta.
X.
Theta will depends on xt for sure. But this perspective is more like after I train a theta, I fix the value. I see the performance of on the population level. It's one way of measuring the performance here.
Okay, I see, but for me it remains a little bit so if we were to describe it in a more rigorous framework,
Mhm.
right?
Mm-hmm.
To say I do the estimation on theta,
Mm-hmm.
yes, then I try to do this kind of estimation with this expectation,
Mm-hmm.
and then for the majorities of the thetas
Mm-hmm.
that I have chosen somehow through my
Mhm.
training, I
Mm-hmm.
really have such a bound.
Mhm.
Is okay.
Let
Okay.
me try to explain this from a different perspective. So first of all, the definition, it's just when I put the statement here, I want to save some space, but in the paper, everything is defined very clear mathematically. For example, this result is trying to say the following. If I can see a total number of n samples, I use those n samples to estimate theta. But I also want to see if there's the n+1 sample. Is it possible that my trained neural network can also give me a good approximation on the n+1 sample that my neural network doesn't see? The neural network doesn't see this sample, but still I want to have my neural network. I want my neural network to have a good performance on the n+1 sample. And this result tells us that it's the neural network is capable of doing that, to have a good performance on the unseen sample that follows from the desired distribution data. This is what this result is trying to say.
Okay, thank you, Renyuan. Thank you again for your very nice talk.
Thank you.
Do we have more questions? If no, let's thank Renyuan again.
Thanks, everyone.
Thank you very much.
Thank you.